We're going to take up one more problem on simply supported beam. Problem number 13. It treats as a simply supported beam, capital AB, of 6 meter span is loaded as shown in the figure. Draw the SFD and BMD. So first, initially we have a simply supported beam at the point A and B. You have vertical reactions at A and B. And you can see from point A, 0 uniformly variable load from 0 at A to the maximum of 30 kilonewton per meter at the point C of 3 meter span, uniformly variable load. At the point D, you have 80 kilonewton acting downwards, which is at a distance of 4 meters from 4 meters from point A. And we have 10 kilonewton meter, a uniformly distributed load from D to B for a span of 2 meters. So the total distance from point B to A will going to be 6 meters. So this is the 6 meter span. So to find the support reactions. So taking the moments about the point A, you are going to get that is the clockwise couple will be equal to anti-clockwise couple. So that means RBV into 6 will be equal to. So now we need to find out the uniformly variable load here. So that will be area of the triangle and the distance of center of gravity from the lower end, because we are taking the moments about this point A. So that will be half into 3 into 30 into 2 by 3 into 3. 2 by 3 into 3. Then plus 80 into 4. Then plus 10 into 2 into 2 by 2 plus 3. 2 by 2 plus 4. So that will be, on simplification, RBV, we are going to get it as 85 kilonewton. Also we have the total sum of the vertical reaction acting upwards will be equal to sum of the vertical reactions acting downwards. So that means also RAV plus RBV, which is acting upwards, will be equal to the downward reaction. So uniformly variable load will going to have the area of triangle. So that is half into 3 into 30 plus 80 plus 10 into 2, which will be equal to 145. Therefore, RAV will be equal to 145 minus 85. You will going to get it as 60 kilonewton. So RAV will going to get 60 kilonewton. So when you have the reactions at RAV will be equal to 60 and also at RBV, which is 85, then the beam will be in equilibrium condition. Now we will going to consider on this beam. So we have to start from the left to right. So we have, first we consider between A and C. At the point A, you have RAV will be equal to 60 kilonewton, and at the point C, you have a 30 kilonewton meter. And then you have from 0 to, at the point C, you have 30 kilonewton per meter. It is the uniformly variable load for a span of 3 meters. Now, what will going to be the shear force at the point A? The shear force at the point A will be equal to plus 60 kilonewton. So between A and C, and or itself at C, if you are considering, then it will be area of the triangle, which will be equal to plus 60. And since the load is acting downwards, so it becomes negative. So minus half into 3 into 30. So you will going to get it as plus 60 minus 45, which will be equal to plus 15 kilonewton. So now you can see that from SF at the point A, you have 60 kilonewton, and SF at the point B, C will be equal to 15 kilonewton. Since it is the area, the power is mm square or the meter square. So since the power of x is 2, therefore you will going to get a parabolic curve. So the curve joining between this point A to this point C will be a parabolic curve. So then we will going to have the bending moment diagram. Between A and C, what happens we will see. SF varies parabolically. And bending moment at the point A now, what will going to be the bending moment at the point A? It will going to be 0. So what will going to be the bending moment at the point C? So the bending moment at the point C will be equal to plus 60 into 3 minus half into 3 into 30 into the distance of center of gravity from the bigger end. So the bigger end is 30, and the point what the moment we are considering is at the point C. So naturally it will be 1 by 3 into 3. So that will be equal to plus 135 kilonewton meter. So naturally bending moment at this point from 0 it will going to meet at 135 kilonewton meter. Since it is the area into the distance of center of gravity, so naturally we're going to get area is meter square and the distance of center of gravity is in meters. So meter cube you're going to get, that means the power of x is 3. Therefore, the points joining between A and C will going to be the cubic car. So the next is consideration from here. After that, we will going to consider, now we will going to consider the span of CD and also at the point D, you have a vertical load. So between C and D, as there is no other load is acting on the beam, so naturally it remains constant at plus 15 kilonewton. At the point D, what happens? Plus 15 minus 80, so you will going to get it as minus 65 kilonewton. So when you are plotting that, you will going to get it as at 60 kilonewton, you are coming to 15. From 15 between C and D, it remains constant of 15 kilonewton. Since due to the point load which is acting downwards is 80, so by convention it is negative. So plus 15 minus 80, which will going to give you minus 65 kilonewton. So it drops to from positive to negative at 65 kilonewton. Now, what will going to be the bending moment at the point D now? So the bending moment at the point D will be equal to plus 60 into 4 plus 60 into 4 minus half into 3 into 30 into 1 by 3 into 3 plus 1. So 1 by 3 into 3 plus 1. On simplification, you will going to get it as plus 150 kilonewton meter. So when you're plotting that from 135 kilonewton meter, you plot to 150 kilonewton meter by means of a linear line, because as there is no other load acting on this beam at this particular juncture. Now we will going to consider the one more span. So that span what you have is 10 kilonewton meter up to 2 meters. So what will going to be the shear force at this point B? So shear force at the point B will be equal to, so minus 65 minus 10 into 2, you will going to get it as minus 85 kilonewton. So from here, when you are considering from D to B, from 65 kilonewton, SF at B will be equal to, it further drops to minus 85 kilonewton. So join between these two by means of a linear line, because it is W into X, where its power of X is 1. So therefore, you are joining between these two as a linear line. Now similarly, we want to, SF varies from minus 65 to minus 85 kilonewton according to the equation of a straight line, which is because due to it is a uniformly distributed load. Now when you are considering for the bending moment at the point B, so BM at B will be equal to plus 60 into 6 minus half into 3 into 30 into 1 by 3 into 3 plus 3, then minus 80 into 2 minus 80 into 2 minus 10 into 2 into 2 by 2 will be equal to 0. So this is how you will going to get from here to here. So what will going to be the nature of the curve? So the nature of the curve when you are considering the uniformly distributed load, so here it is W into X into X by 2. So therefore the power of X is 2. Therefore in joining between from 150 kilonewton meter to 0 will going to be a parabolic curve. So this is how you can be able to analyze this problem on bending moment diagram. So you can see at the point D, SF changes its sign from positive to negative. So therefore, at that particular point, you should have a maximum bending moment. So you can see that the maximum bending moment at this point will be plus 150 kilonewton meter. So maximum bending moment occurs at a point where SF changes its sign. SF changes its sign at D. Therefore, at that particular point D, you will going to have maximum of 150 kilonewton meter. So it is quite evident from the figure. So this is how you will be able to get the final solution. Thank you.